For this problem, we are interested in minimizing the time it takes Lassie to reach the drowning person at point B. We have to take into consideration the time difference in Lassie's swimming and running speed, in which path is most optimal. For the first part, we are given that r is the speed at which Lassie can run, and s is the speed at which she can swim. We are also given t of y, how fast it takes the dog to reach the drowning person by running to point D before entering the water and swimming to point B. With this information, we came up with this formula. For this equation, x, y, and z all relate back to the original diagram and the distances shown. Specifically for z minus y, this indicates the region of beach lost where Lassie jumps into the water. And this part of the equation indicates the length Lassie must swim. Additionally, we know that time equals distance over speed. So if we add the two speeds, swimming and running, together, we will be able to find the time it should take Lassie to reach the drowning person. Now to look at different situations of R and S, we found that the time to reach the drowning person would only change with relation to distance. Because of this, we must take the derivative and set it to 0 to find the minimum time needed, and thus which path Lassie should take. Our derivative is as follows. And now after setting it to 0 and solving, we find this equation. As stated above, we can use this equation to find the value of y that minimizes Lassie's time and optimizes her route. Now considering the different scenarios of s and r, first starting with r is greater than s. When this occurs, we get a positive number for which is possible to take the square root, thus giving us a positive y value. For the opposite situation, r is less than s, we get an opposite answer, a negative square root, also known as an imaginary number. In a situation where r is equal to s, we end up with the square root of 0 in the bottom of our fraction, giving us an answer of undefined. In conclusion, we will only be able to compute an answer that works for this problem when the running speed is greater than the swimming speed.
Okay, so continuing under part 2, we were asked to determine the relationship between distance of x and y. So here we're actually given actual inputs for both r and s for the dog Elvis. So our first step was to compute the averages of both running and swimming times, r and s. So we then took the distance here, and then we divided it by the average time that we were giving in the chart there. Like for example, for r, we did 20 meters and we divided it by the average, and we got 6.35232 meters per second. And then we did the exact same thing for swimming, s, but with the respective numbers. So then, and in that case, we got 0.872. So here we have this following equation using the derivative of ty. And then next we're going to set this equal to 0. And then when we set to 0, do all the math on there. We get x equals 0.139x. So with this equation, we can see that the relationship between the minimized time with the relationship between distances, again, y and x. So this equation also allows us to find at which point along the beach Lassie should jump into the water and start swimming, which happens to be most of the beach is running. So additionally, we can see that distance y is roughly going to be 1/10 of the distance of x.
This is Miles Munson speaking, and I'll be covering part 3, where we're asked to determine if Elvis innately knew calculus. We did this by creating a graph in Excel with the data points that we were given for part 3 and set it against the equation found for the relationship between distances x and y. These blue dots here represent the Elvis data that we were given, and the red line that runs along here is the optimization relationship between distances x and y. Looking at the graph, we can see that Elvis's data does seem to follow the trend line of our equation, specifically from roughly around 5 to, I would say, around 12 distance x. We can see a trend, though, that as the numbers increase past this point, as they get closer to 15 and 20, that they fall away from the trend line and show that Elvis jumped into the water much sooner than would be optimal. However, because much of the data does seem to follow the line, we can conclude that Elvis does seem to have a quote-unquote innate ability to do calculus, meaning he was able to optimize his path and time taken to retrieve his ball, which also means that Lassie would most likely be able to have similar results and reach a drowning person using an optimal path.
In this final part of the project, we're going to be talking about limitations and assumptions that the project made. So there are definitely limitations to this experiment. First, being the dog that was tested, it is most likely not a spokesperson for every dog out there, as there are different breeds more accustomed to running or swimming. Additionally, we assumed that the running and swimming speed was constant, and that Elvis or a hypothetical Lassie never got distracted or strayed off course. In the real world, we would have to account for the unavoidable tiring of the dog and work into that problem. Other examples of that could be distraction or loss of interest in the ball. This could have been done if someone was taking the entire time the dog swam or ran, rather than gathering the data in the way that was accomplished. Second would be Pennington's method of data collection. The issue is that he was running after the dog as it ran and taking measurements alone. As mentioned earlier, it would have been better if there were extra pairs of hands during the data collection to cut down on human error and guarantee better quality in data, such as someone who could place the stake or be next to the ball to take better measurements. Third is that Pennington only tested on a calm day and only once. This is similar to assuming everything is constant, and we cannot know how inclemented weather would affect the dog's ability to optimize its path. Therefore, even though these limitations were present, we can assume that Lassie and dogs in general are capable of calculus.